Good afternoon, participant friends. The speaker for this session, Professor Datta is here. Welcome, sir.
Thank you, thank you, thank you.
Yeah. So I will introduce him for this session. Dr. Datta has obtained his PhD degree in physics from Savitribai Phule Pune University, formerly University of Pune, India, in 2008. He was a DST, Nanoscience and Nanotechnology postdoctoral fellow at JNCSR Bangalore in 2008 to 10 with Professor CNR Rao, and then at Material Science and Engineering Department, Northwestern University, USA from 2010 to 12 with Professor VP Dravid as IUSSTF fellow. He was awarded a prestigious Ramanujan Fellowship in 2013 and Young Research Scientist Career Award in 2014 from Science and Engineering Research Board, Government of India. He is also a Fellow of Maharashtra Academy of Sciences and the Fellow of Royal Society of Chemistry, FRSC, London, UK. He was listed as a top 2% scientist from world by Stanford University, USA in applied physics in November 2020 and again in October 2021. Dr. Latte has published more than 210 research papers with more than 13,500 citations in peer-reviewed journals with current H index 49 and I-10 index 151. He has edited 2 books, filed 14 patents, and also a member of various scientific societies across the globe. He is also a board member of various international journals and associate editor of AIP Advances USA and RSC Royal Society Open Science UK journal. He has completed several major research projects funded by various funding agencies. He has survived and supervised and co-supervised 6 PhD and 20 master's theses. He has delivered more than 100 invited talks in various national and international conferences. He has visited several countries for the purpose of research work and attending the conference such as USA, Canada, France, China, UK, etc. He has organizing national and international conferences held in India and abroad. Currently, is working as a head Center for Nanoscience and Nanotechnology, Amit University, Mumbai, Maharashtra. His current research work focuses on development of 2D hybrid materials for nano and optoelectronic devices, energy generation and storage applications. He is a leading expert on Raman spectroscopy to characterize a wide range of carbon and inorganic 2D TMDS based nanomaterials, their thickness, temperature, and pressure dependent studies. With this, today is going to speak on 2D nano hybrid materials for a novel device technology. With this, I request Dr. Datta to take a charge of this session. Over you, sir.
Yeah, thank you, Professor Bhaskar, for a nice introduction, and also thank you for kind invitation to deliver this particular lecture on FDP, especially for nanoscience and nanotechnology, organized by your department and your university. It's nice to have deliberation for this particular time. Thank you for your introduction and invitation as well. So, yeah. Before I just start, I'd like to thank all the funding agencies who have supported our research. So supported for fellowship to our PhD students and project assistant from CSIR, DST, ACRB, and all other funding agencies. Let me take this opportunity to thank our collaborators from India as well as collaborators from international collaborators from various other countries. Let me take this opportunity. You all are welcome to submit your research paper in AIP Nanoscience, where I am serving as editor board and associate editor. The impact factor of this journal is currently 1.57, and this journal accepts papers from physics, chemistry, interdisciplinary field like biology and all these things. So this particular journal is very good, and of course it is American Institute of Physics, and you are welcome to submit uh, paper to this journal. And first to submission to first acceptance time is actually 62 days, and within acceptance of the paper is available online to all. But remember that this journal is particularly open access and has publication charges. In uncertain event, the publication charges also can be waived for some of the researchers who do not have funding supported on this. So publication charges also can be waived off for that particular research. So another journal from RSC, especially Royal Society of Open Science, also again inter open access journal, and current impact factor of this particular journal is 2.5. It's good journal, and those who are doing research in chemistry related areas, they can submit full research article, review article, perspective, maybe a short report, or maybe some replication, evidences of some synthesis, comment, and anything like invited review article and all these things are also welcome to submit to this particular journal. Another journal which is known as electronic structure. Again, this is by IOP London, UK. And currently we are actually reading one special issue on nano optoelectronics. The submission date is coming soon, this month end. And we are also in this particular journal covering electron. Basically, this is for electronic structure theory. Maybe some experimental work also can be published in this particular journal. Again, we are expecting multidisciplinary research spanning material science, engineering, physics, chemistry, biology, and all these things. So currently, the editor-in-chief are these two guys, Dr. Professor Bert D. Jong and Risto Newman. And impact factor of this journal is expected to be 3.2 in another few months. And similarly, another sister journal of this electronic structure, which is IOP. So we are currently third year of this publication. So we're also expecting similar kind of impact factor to be come in another few months, in maybe I think May, June. And it's also a very short publication. Maybe you have some short result, very important research you want to publish. So where you can publish. So this is a very particular journal where you want to publish one or two figures, and very important result you got some anything related to physics, chemistry, biology, and all this. Again, interdisciplinary journal, and you can publish. And here, submission to first decision is within 10 days. So this is very important when you want to publish your research work within a very short time. So this particular journal is very important, and there is a currently this is also open access journal, but there is no publication charges. So all are welcome to submit your research article, a very short research article or very important result which you want to convey to the world. So all are welcome to submit research paper to this particular journal. Again, I just start all slides presentation with this motivation. Achieving success in science does not depend on how where you are located. It depends basically on how you dedicatedly do that particular work, availability of your time, excellence of your outcome or whatever result, and how you present your result to the international community. So that's very important. to go ahead with the success in science. So what are the facilities available with our laboratory? We have this particular facility, like we have optical microscope, we have chemical vapor deposition system, we have gas analysis system, we have photolithography, based on photolithography system, where we can develop 10 to 100 micrometer devices. Of course, we have also stainless steel mask. So we put the mask and you deposit the film. So directly we get the device. Also, we have photostat, galvanostat for measurement of supercapacitor and kind of batteries. Also, we have state-of-the-art facilities for electrical characterizing measurement, maybe. Then we have thermoelectric measurement setup. Also, we have very expertise in the area of gas sensing analysis. So we do a lot of gas testing based on NO2, ammonia, hydrogen, and all kind of alcohol, maybe some poisonous gas. So we have this state-of-the-art facility. So we can go up to maybe 10 ppm. That is the limit of our system where we can detect this particular concentration of the gas. Also, we have experimental setup for hydrogen generation. So hydrogen is going to become very crucial and important for coming years to go. So it's very important. There are many issues and you have to address. For example, how to generate hydrogen, the energy needed to, for example, if you want to get hydrogen from H2O, then the energy required to break the bond between hydrogen and oxygen, that particular research. And once you have hydrogen, then issue of storage. So storage is also important. Once you have hydrogen, you need to store it, right? And once you have stored it, then how to utilize that hydrogen? Again, you have to recollect that hydrogen from wherever you have stored, right? So this particular research is very important, and government is also supporting energy-related research, not only in hydrogenization but also solar cell, solar battery, supercapacitor, and all other fields. So particularly working on 2D nanomaterials as a catalyst for breaking the hydrogen and oxygen bond to have a hydrogen as a fuel for the next generation. So this is the typical setup which we have in our laboratory. For example, you have set up, and then the particular is hydrogen is collected, and then it will be measured and analyzed further. Also, we have a solar simulator. For example, again, the measurement setup consists of which can calculate efficiency of the solar cell, fill factor, then how much is the short circuit current density, open circuit voltage, and serial ballistic resistance we can measure. We have a particular glow box to deposit the device or make the device and finally test the device. Of course, our current research mainly focus on 2D hybrid nanomaterials and related other fields. So when you talk about 2D hybrid nanomaterials, so as a center of nanoscience and nanotechnology, we look around all the subjects like chemistry. So synthesis is going to become very crucial part of the material, any kind of material, not only 2D materials, any nanomaterial or any material science synthesis. So you click that chemistry is very important. Click chemistry is very important, or any short chemistry where you can generate a material in bulk quantity. Any material you can get. So because finally industry needs, okay, so they're not sustained with a 1 gram of your sample, few gram of your sample. They need actually sample in kgs and tons when you want to make it large scale and industrial scale. So that particular research we are doing, but not on that particular scale, but we are currently working with 10 gram or something like that. And of course, when technology is there, we collaborate with a lot of industries around Mumbai and all. So I have a very good response, and they are also going to make the materials on mass scale or depending upon their need. Also, look, when the material is done, characterized or synthesized, we think always, so what we can do with this material. So can you do some chemistry? Can you use this material for say particular device? So can you see the physics of this particular material and use for some novel device application? So can you design a material, or can you design a device based on that particular material, or can we have a design material or novel material or functional material, right? So that functional material can you whatever function you want. For example, I want a very good sensor to detect 1 ppb of hydrogen in at room temperature. So that's also become a very crucial part for room temperature detection of any kind of gas. So this technology is still not yet available in the market, and we're also working on this particular technology where we can fabricate a device which can function at room temperature. So normal the sensors which are available in the market, they are oxide based nanomaterial sensor, but they require actually high temperature. Of course, advantages they have very good selectivity, sensitivity, and all other factors. So here there are some limitations, and we are actually working on the modification of the material, the functional materials, so that can give you a better result than whatever the oxide materials gives. So of course, we see what are the medicinal application of this particular materials, for example, 2D materials like MOS2, graphene, and all these things. So of course, we have a lot of collaborators. They know, for example, for biological application, can this material used for antibacterial application, gram-positive bacteria, gram-negative bacteria, and all these things. And of course, our whole heart is physics. Can you have transparent devices? Can you have transistor with gas sensor, solar cell, and all other kind of device applications? So when you talk about the our another 4 years research, so we actually completely focus on 2D materials for again nanoelectronic devices, materials for coating technology. Again, lot of industries are involved for coating and all this technology. Then I also have research on energy storage, supercapacitor, batteries, and maybe depending upon the industry. So can we contribute to the requirement, industry requirement? Of course, one of the area of research just discussed is the hydrogen generation and storage as well. So we talk about a smart car or driverless car. So how many sensors is needed? So these are the list of the sensors that are needed to have a driverless car, and it is expected that in another 15-20 years, driverless cars will be available in India. Of course, now it is available in USA. In particular cities, it is available. So we are also working on a kind of sensor, for example, fire safety sensor, sensor number 22, fire sensor. We are working on this particular sensor. And when you talk about the sensor, what kind of technology is needed to develop when the sensor is going to market? Of course, we are working on 2D nanomaterial based fire sensor, basically to detect maybe that again the similar kind of gases, NO2, carbon dioxide, carbon monoxide, and all these things. So when you talk about the device technology, of course, we need to think how we can control growth or how we can grow the material on large scale as well as maybe thickness dependent large scale materials, maybe one layer, two layer, or few layer, depending upon the material thickness, which gives very good sensitivity, selectivity, and other factors. Of course, once we have grown that material, then we have to integrate all other signal processing. Then we need to see, okay, pass the various tests. Like when the car is coming to market, we need to that car need to have certain tests to be passed. Then only then it come to the market, right? So similarly, this device also need to satisfy some of this criteria before coming to the market or before it can be fixed to the car. Of course, one of the problem is fabrication techniques, because large scale fabrication we don't, because we have to fabricate millions of such devices when we want to put it into car and other applications. Of course, once we have fabricated devices, then packaging become very important, because when we want to sell this particular devices into market, we have to package the device and we have to integrate the device so that it has certain lifetime. Because once you have purchased the device and lifetime is very low, then it's of no use. So if it is very good, then it will give you very nice device fabrication, right? For example, what technology we are also doing? We are also working on cell power flexible and variable sensor for cardiovascular disease prevention. Again, one of the societal problem which we are covering, low cost sensor. For example, a lot of people in India, they are suffering from this particular cardiovascular disease, right? So what we need, what we have identified a device. So we have made a device based on 2D materials. Of course, this is in testing phase. And we want to charge this device on our cell movement. Because suppose I want to put this device on hand, and I just, depending upon my hand movement or depending on my body movement, it will be self charge. And therefore, this is flexible, I can put it anywhere, and this is variable. So anyone can wear this particular device, and that will give you some kind of signals where the person has cardiovascular kind of characteristics or not, right? And then of course these are again low cost sensors. So we want to make this device with less than 100 rupees, so that anyone can afford this particular device. right? Of course, we're also working on these chemical and biosensor based materials. So again, this is industrial need, and of course, people are working on this is a particular need of the country, and also working on the remote health monitoring system. Now the COVID has given a very big lesson how we should be alert with our health. For example, we're also working on a system where these particular devices are kept on the body of the suppose this person, and this person has this particular lot of sensor devices. So for example, something happened to this particular old man. So what happened? He has mobile, and so it will be located by this kind of GPS communication system, and then message go via internet to his family, as well as to the clinician or hospital, as well as the one message will go to the emergency car, and then it will come that ambulance, and maybe life of that particular person will be saved. So again, this is automatic. So sensor will give you the information. Oh, this person has heart rate, respiratory system, and all these things. So cardiovascular disease and all. He has fall down or something like that, depending upon the pulse and all these things. So this communication will become very fast. And once these things happen, of course, we can save a lot of lives, not only in India, but of course, worldwide. So this is the current data up to last year. So each year the national healthcare expenditures are rising by 2% faster than GDP. So this is data from National Health Education System from America, WHO. And this data tells that each year, healthcare system is expanding because population is increasing every year. So this particular field is very important, and there is a rise in the. And COVID has told us that we need to have a very alert for all kind of. We need to ready for all kind of these situations. We need to ready for fighting with any kind of healthcare related systems, and our healthcare system need to be improved lot, right? So, and we are not in that position currently because of the economic system and other field, and the cost of the devices related to. Once we have reduced the cost of these devices and testing, definitely we are going to increase the healthcare system better than America and Italy, right? So we have tested some of these materials, of course, again based on 2D nanomaterials. Some small devices we have made and tested at the laboratory scale. For example, we have made these sensors. Again, these sensors are like flexible sensors, so they can be attached to the skin. Okay, anywhere it can be kept. So what parameters currently we are looking? For example, okay, I have flexible sensor kept on my hand or any part of the body. So I can continuously monitor ECG, skin temperature, skin elasticity, skin strain, pulse rate, blood pressure, maybe blood oximetry. So these kinds of things I can always measure through all throughout the time, and it is also connected to mobile or any kind of Bluetooth system device, so that will give you the correct signal of my body. And again, depending upon the situation, it will give message. And how we will collect the sample? So maybe activity, skin temperature, stress, emotion, organ function. Maybe smell also can be tested. Some of the in cases breathe hydration also can be tested. And what kind of things we are expected? So we are expecting biomarkers to be changed, or pH can be changed, locate, or glucose level has been changed, and all these things. So what kind of devices or sensors we needed? So we have biopotential electrode, we have temperature sensor, we have strain sensor, change in resistance, and maybe change in capacitance, whatever. And maybe also have pressure sensor, also have humidity sensor to see the how much is the humidity level, and maybe you have biosensor to check okay how much is the glucose level and all these things. So we are working on currently the flexible devices based on this particular material. For example, what we need, so we have this particular like it is already available in the market, right? So only thing is that it is not affordable, and cost is very high, and so we are in the position to have designed a particular device with low cost, and of course it should be one day it will be available with the cost of 100 rupees, so that everyone can get that particular device and they can measure. Hello, Bhaskar, my sound is okay? Hello? Can you hear me? Hello? Can you hear me properly?
Yes, yes, there is no problem.
Okay. Please, I was getting message that there was maybe I will just switch off the video and yeah. Okay, yeah. So this is very important, and again, the motivation is to design a device with very low cost. So also, this particular ring is already available in the market. So it's a pulse oximetry ring, and it monitor oxygen. Oxygen become very crucial in this particular COVID time. Oxygen level, monitoring oxygen. When we go to hospital, then at that time only we are knowing that how much is the oxygen. Of course, now the oximeter is available with 2000 rupees or something like that, or maybe less than 2000 rupees. We will never care about the oxygen in our body. It is very important. So, can you monitor oxygen throughout our lifetime? Okay, if something happened, some alert happened, less than say 90% or something like that, we can immediately run to the hospital and get corrected that oxygen level. So this particular ring is already available in the market. So this continuously monitor your oxygen from the body and give the signal, or maybe connected again Bluetooth to mobile. And mobile you continuously monitor. Okay, tell you the how much is the oxygen level in your body. Okay, right, and then if it is fall down in some particular level, you have a like every day alarm you are keeping a mobile, it will give you alarm. Oh, your oxygen level is going down. You please run to the hospital, right? So basically, it is based on the principle of blood pressure pulse, which causes spatial one displacement. That's very simple physics they have used, right? Again, how much is the blood volume changes by this particular photoelectric method or photoresistance is again simply measured, and that gives you how much is the oxygen level in the body. Again, what are the healthcare wearables devices already available in the market? Again, so these are many wearable devices already available in the market, and this is I think 2 years data which I have. And most popularly consumed with you see this is important figure which given by again WHO. 34.25 million people already sold into the world, right, by 2019. So I have not given the data of not 2020, 2021. COVID time data I have not given. You just imagine how much market is available for these particular devices, particularly healthcare based devices. Again, people are always preferring variable devices because we don't have to care. Okay, you can keep it into our body, right? We don't have to care unless we have once you wear in the morning. Up to evening, we don't have to care. Okay, where it is and all these things, right? Like clock we wear, right? Like that. And then, of course, it will continuously monitor your body metrics and gives you the accurate figures so that we can more care about your health. Okay, so and this is just the beginning. So what are the other sensors it has been in the market? It's already into the market. For example, lung cancer sensor, again, very important thing. Then smart bra already available in the market. So you can continuously detect the case cancer and cancer related diseases, right? Again, thermometer, skin-like devices. Already just put your powder devices. So color of the device is like skin. So nobody can identify me. Oh, they have kept the device and all this. Again, it is a flexible, cloth-like structure, very thin in layer, and of course, it is continuously functioning and charging based on your hand movement, self-charging, self-flexible device, and all these things, right? And this is very important, particularly again. A lot of people are again wearing this fitness particular tracker, Fitbit, band, and all these things. So this gives you many accurate information about our health and all these things. Again, this is smart wristwatch. So that will also give measure pulse, again, oxygen level, pulse, whatever the information is already available. So for example, another things, flexible variable sensor for health monitoring. You can see these are actual pictures of the devices. They are mounted on the hand. You can see and the color of the device, the thickness, and all these things. So this is again flexible. Depending upon your hand movement, it will charge, and it does not have such a side effect. Okay, once you want to remove, now just like you are putting some statue on your body. So it's a similar thing. You put a statue on your body, a device statue, nanomaterial based device statue, and then this will continuously monitor your health parameters and metrics. So it's a very important parameter. So, for example, I have made this device here. This again based on single wall carbon nanotubes, P dot PSS. So, we wanted to monitor what happened. The device is kept near to your mouth and just forehead. You can just see figure. Kept the device in front of this forehead, and we put the device near the mouth. What happened? You have measured the signal. For example, you see the resistance have been measured when a person is laughing. Okay, see how much is the change in resistance. Okay, person is not laughing here. Person is starting laughing. You see how much is the change in resistance. Again stop. Okay, again started laughing. Again stop, and how you see how much is the change in resistance. Similarly, you see how if the same person is crying. Okay, see how much is the change in resistance. Here you can see the change in resistance is just no 0.6 no 0.6%. Okay, see how much is the change here? Almost when person is crying, change in resistance is almost 200%. Right? Now, the same device I have kept near to the mount. You see how much is the change in resistance? Here, change in resistance is say 40%, and here change in resistance is 0.2%. So we need to continuously monitor, maybe analyze and continuously see where the device need to kept, and we need to optimize the parameters. Once we optimize the parameters, then we can easily identify what things are happening in your body. Right. So this is another particular nanomaterial based device based on again graphene like materials and maybe some kind of nanofibers. So all the devices based on the principle of either piezoelectric, pyroelectric, piezoresistive, chemoresistive, or thermoresistive, or photoresponsive, or electroactive device. We can see electrometer, transparent material, stretchable material, and stretchable devices. So this is one of the approaches to make the composite nanomaterial based device. So there are many approaches. For example, another approach maybe we have stretchable, transparent, ultra sensitive, very highly sensitive device. So anything small change happen in a body surface, temperature has been changed by 1 degree Celsius. So that will also detected by these particular devices. Again, these are self-powered. So with your body movement, they will charge and strain sensor, and they will be actively monitor your body, all kind of parameters on the body, so that you can continuously monitor your health. Right? So this is the complete motivation. And again, you can see the devices which we have made based on again supercapacitor. They can be charged on supercapacitor. This is the next generation devices. So we can charge or have turbo electric nano generator. Again, with the movement you can charge the device and strain sensor. So this is also another area of research where you can measure lot of strain parameters. Strain, how much is the strain generated when you give the resistance. We can measure resistance as a function of strain, and many other parameters can be monitored and measured. For example, this particular device which I was shown earlier, this is based on again single wall carbon nanotubes, P dot PSS, and PDMS mass kept on it. You can see how much is the transmittance of this particular device. You can see almost device is 60% transmitted. And once you can have strain, how much you can stretch the device. Okay, you can bend the device. You can see bending as a function of or change in resistance as a function of strain. So I am straining the device say from 10% to 100%. I completely now stretch the device. Okay, how much is the change in resistance? So this particular parameters are important to monitor. So I can also measure gas factor. What is the function of strain? So many parameters I can measure, monitor, and again, of course, I can optimize. Once I optimize, you can see how many cycles this particular device can be run. So we find that the such devices can be function of 50,000 cycles. You can see almost the lifetime of man, right? Many 50,000. So many years we can use this particular device. So again, what other parameters can be monitored or measured? So these are many parameters that can be measured, monitored, maintained. Now, for example, if you want to have self-powered device, because you don't need battery and all these things, so this will be charged on its own, depending upon your body movement and all these things. So we also tested, okay, how many cycles it can be tested, right? How many cycles it can be tested. For example, we have device again based on this particular carbon nanotubes and the PDMS mass. We have tested how much is the change in the discharge circuit current. So we found that after 1,000, 3,000, 5,000, 7,000, 9,000 cycles, the stability of the device is almost similar. And you can see, you can also charge, discharge device, and almost are getting very excellent result based on this particular materials. Again, this is based on single wall carbon nanotubes, and also the PDMS or P dot PSS and other polymers also. So, for example, once we have all these things in your hand, so we also need to optimize sensor integrate variable sensor electronics. So we need to work with again a lot of collaborators, those who are expert in software, materials, device fabrication, packaging. Again, we need to take help of this biomedical engineering, how to monitor these particular devices on the body surface, right? And of course, circuit communication. So these are also important. So basically, this is interdisciplinary field of research, and it has a lot of field markets to industry, and a lot of things can be done in this particular area of research. So what we are doing currently, we are actually going a large number of 2D materials from graphene like inorganic layer materials, then 2D chalcogenoids, then amexins, and lot of materials were growing in your material laboratory. For example, also working particularly functional materials. Materials have a lot of functional applications. So that we call as a functional materials, right? So interdisciplinary applications. Once we have grown this material, of course, our aim is to grow the materials on large scale, large quantity, right? Once we have done this thing, so visualize these material properties like physical chemistry, material chemistry, a lot of this physics, chemistry, their properties, then quality, crystalline quality, whether the material is crystalline, polycrystalline, or any other amorphous and all these things, then where this material can be fit, where this material can be used. Or once we have these things, crystalline quality and all these things, so we are also working on layer stacking, layer dependent properties, layer dependent applications. Because maybe one layer of graphene may be suitable for detection of one atomic, one molecule, but maybe three layer of graphene may not be suitable, right? So that particular application we are also looking. So maybe because graphene has certain disadvantages, like band gap is a problem, and there were people are looking at the materials with a band gap, natural band gap. For example, this 2D chalcogenoid semiconductors. So this they have already a band gap, and then band gap can be tuned depending upon thickness. And this material has a lot of potential applications. So once we have this layer stacking, we do a lot of optical properties measurement. Like then once the material is tested or satisfy all these condition criteria, of course we do mechanical testing. And then once this testing is passed through mechanical properties and all these things, particular level, and then we'll do go for the electronic measurement, this change in resistance and change in capacitance, then all other properties, field effect transistor, gas sensor, and all these things. So this is the traditional things to grow any kind of materials, not only MOS2, WS2, lot many materials we grow in our laboratory. So what message or what things you will take today from my next maybe 1 hour or 1 hour 30 minutes. So maybe how can synthesize these materials in a small scale, in a small laboratory where there is not much facilities required. How we can characterize these materials, graphene and graphene-like materials, and what applications we can do it in your the facilities which we have available. Okay, once we have graphene materials, because graphene has certain disadvantages and maybe application point of view. So can we have a graphene like other materials, and what are the material, these materials, and how we can grow these materials, how we can characterize these materials, and how we can utilize these materials for certain applications. For example, then how we can combine these materials, 2D heavy materials. Maybe you can how you combine graphene like other 2D inorganic materials, maybe graphene with oxide materials, or graphene with amazing materials, or graphene with some other materials. So that has some functional application. So these materials we call as a hybrid materials. And how we can utilize these materials for novel technology, novel application, and all these things. And finally, I will end with the rise of this today amexins for novel devices, because they have been recently found that they have been used for this particular application of charge storage, maybe supercapacitor and battery. So how this material can be synthesized, and how we can characterize these materials, and how finally we can use these materials for novel device applications. Okay, maybe many people here are know about graphene and about graphene properties, their application of this. I'll just give you overview how this graphene and graphene properties can be monitored, measured, and synthesized. For example, everybody knows that graphene is a kind of seed, right? Seed of this benzene ring connected to each other, right? So this large seed will become one layer of graphene. And it is said that graphene is mother of all graphitic forms because so you can see the moment you can now for this graphene seed, you will get the zero-dimensional buckyball. Okay, you can roll the seed, right? Okay, once you can roll the seed, you will get the one-dimensional carbon nanotubes, and you can put actually stack one graphene layer to each other like that, like paper bundle. You will get original three-dimensional graphite. So therefore, graphene is known as mother of all graphitic forms. Also, it is used as a starting point of calculation of various carbon-based materials, right? And this particular material have been studied more than last 60 years, right? So there are a lot of challenges for synthesis and all this thing. And this particular material, first time discovered in 2004 by AKG Manosola at University of Oxford in UK, and they have been given Nobel Prize for this very simple groundbreaking research because they found that when the moment you make this monolayer of graphene, it becomes very highly conducting and gives very high fluid mobility. Okay, what are the properties of graphene? For example, it is found that it is the world's thinnest object ever obtained because thickness of one layer of graphene is almost 0.34 nanometer, and the Young's modulus, which they have measured, 1 terapascal, which is more than. It is found that the graphene is 200 times stronger than steel material. So this is very important. Then again, more stretchable. Young's model is very high, more than 200 times of the steel. And when you talk about the property of stretchiness of the material, we can easily stretch the material, right, up to 20% elasticity. Again, the mobility, the conductive, the carrier, basically carrier mobility is nothing but the speed with which electron can move in a particular material, right? So that's the mobility. So mobility gives 10 raised to 5 centimeter square whole second. That means when you use these devices, for example, in nanoelectronic devices, the speed of the device is so fast, right? That is the one of the application of these graphene-based materials. For example, again, this particular material can be impermeable to any molecules. Means it can be used for hydrogen storage. It can be used to store any kind of molecules and all these things. So this becomes very important. Okay, and the structure of the material is very stable and it is carbon, right? Low cost. Cost is very small and almost transparent, 97% transparency and low cost. Again, the density of the material is 2 gram per centimeter cube. It's very important. Shown you here cartoon of elephant. When suppose I have one graphene sheet, and if I able to put one pencil on any pointer thing, and on the pointer thing, if I able to put one elephant, still I cannot stretch that graphene sheet. You can imagine how strong is this particular material, right? Okay, so while again graphene becomes very important, so this is just like physics or chemistry, where graphene becomes show very important unusual properties in most of the materials. Either they are semiconductor, they are insulator, or they are metal. In metal, when you talk about the band structure, in metal, the valence band and conduction band, they are overlapping to each other. In semiconductor, there is a small gap. In insulator, there is a huge gap. Therefore, they are insulator, they are not good conductor. Here in graphene, the conduction band and valence band, they are just touching to each other. So this particular point, which is known as K point or Dirac core, where the conduction band and valence band they are touching. So this particular band structure gives a very unusual physics or chemistry. And when you pass current through this material, you get the current in both the direction. You apply a positive voltage, get voltage. You apply negative voltage, still you get the current in the channel. So this is unusual for found in this particular material. This was never found earlier in any other material. So and of course the conductivity is at room temperature. That is also one of the advantage. And this gives lot of unsolved problems which earlier found in physics and chemistry. So we are getting answers of all these problems. You will see the direct solid again because of the band structure. We have a lot of very high speed electronics. Energy of the electron is again linearly dependent on the wave vector, and which is near again this symbols like k naught and k, and particularly in this billion zone. So this found that when the conduction band and valence band they are just touching to each other, so there is no gap. So this is known as zero gap semi-metal or semiconductor, whatever you want to say, because here there is no band gap, so the band gap is almost zero. So this is known as semi-metal. So this doesn't follow the property of semiconductor, neither metal, because metal conduction band and valence band they are crossing each other. In semiconductor there is a gap, insulator almost huge gap, and in this particular they are just touching to each other. So we call this as a semi-metal. Again, this gives very energy properties. When you apply negative gate voltage, we have current in the channel. We apply positive gate voltage, still we have current in the channel. And this gives p-type semiconductor and n-type semiconductor behavior. This is known as electric field graphene, and this particular effect, which is known as ambipolar field effect transistor, because both the time we have p-type and n-type conductivity in your channel. So how much now? What is the speed with which electron is traveling in this particular material? So this is very simple energy equation. I'm sure you all have studied in the 12th standard. So what is this particular equation tells that H square is equal to m square c raised to 4 plus p square c square. Okay. So here m is the mass of the particle, and of course here we have electron. Okay. C is the velocity of light, right? Okay, P is the momentum, and again C is the velocity of light. Alright. See, when electron is traveling in a particular material with very high speed, okay, here, okay, electron has mass. If it is moving very high speed, then it behaves as a massless particle, right? Because of the speed, it is moving with very high speed. Therefore, it is behaving as a massless particle. Therefore, here m is equal to 0. But actually, electron has mass, right? Because of the speed, it behaves like a massless particle. Therefore, E is equal to Cp, means the velocity of electron which is passing through this graphene sheet is directly proportional to 1 upon 300 times the velocity of light. See how graphene electron is traveling through the graphene sheet. So this brings us unusual physics and chemistry, and this gives lot of application in electronic industry. Okay, how you make graphene? Okay, this particular, okay, I have, for example, this is very simple thing. You just get the graphite crystal, which in actually, of course, I need very high quality crystal, because if you want to get very good layers of graphene, and then I need actually. So, how much is the thickness of this particular printing paper, which we have in front of you, right? So, printing paper thickness 0.1 millimeter, which is, if you convert it into nanometer, you can see 1 lakh nanometer, right? So I just want to slice down to one atomic plane of graphene. Okay, so what we need actually, I need this particular graphite crystal. I need this magic scotch tape, which is available in the market with 5-10 rupees, and I need actually SiO2 Si substrate. Okay, and I need actually again simple optical microscope, which is available in your institute, any particular biology laboratory. And once I have this particular graphite crystal type SiO2 Si, so I particularly need 300 nanometer thickness of this particular SiO2. Of course, any kind of thickness is fine for SiO2, but this 300 nanometer SiO2 gives very bright contrast on your silicon dioxide substrate for these graphene sheets. So I can easily identify under optical microscope how much is the thickness of one layer, two layer, or multi-layer graphene. Okay, so what we will do? I will take this HOPG crystal or graphite crystal, whatever available, and I will put the scotch tape or any type of transparent tape on this particular graphite crystal. I will put this tape and I will take it out. I will beat that tape repeatedly few times, maybe 5-10 times, And then once I have built the tape on each other, then I will put that tape onto the SiO2 substrate, which already I have created any size, maybe say 1 centimeter by 1 centimeter, whatever, depending upon your need. And I can slightly put that, rub the tape on top side and take out the tape from that SiO2 substrate. And I will straight away go to the optical microscope and I will see. So I can see all these things color contrast under optical microscope. Okay, you can see this is monolayer and all these things. These are multi-layer samples. Okay, so and of course I can do atomic force microscopy to confirm how much is the thickness of each individual layers, and found that okay, this particular monolayer of graphene having thickness of not less than 0.5 nanometer, because one layer of graphene is 0.34 nanometer. So this is confirmed that the thickness of the monolayer graphene is so this is one layer of graphene. So this I can confirm. Okay, and then again I can do FEMAT at elsewhere and find out how much is the thickness, and depending upon thickness I can tell okay how many layers are present in that particular graphene flakes. Of course, I can go and do very important study by Raman spectroscopy. Okay, you can see here another image which are taken under optical microscope, right? You can see this particular one layer of graphene is almost transparent in color, almost transparent color. So thickness of this particular layer is almost 0.34 nanometer theoretically, right? The moment move from one layer to two layer, you can see there is slight contrast has been improved. And go for three layer. Of course, you can go here. This particular very light and dark color. These are multi-layer, and these are maybe more than 10-15 layers of graphene. Okay, so just simple optical microscope, you can identify whether graphene sample is one layer of graphene, two layer, three layer, or multi-layer. So this is advantage. Well, suppose graphene synthesis by a very simple chemistry method. For example, you have graphite powder. So what you can do, you put this graphite powder in the strong acid such as H2SO4. You have oxidation. Okay, once we are done the oxidation, so you will get the graphite oxide. Okay, so do mechanical explosion or thermal explosion. Means you can heat the this particular graphite oxide at high temperature. So you're done, you will get the single graphite oxide layer, right? And of course, we need to reduce it because you have a lot of functional groups. So hydrazine is very good reducing agent. You can of course reduce this graphite oxide to have a single layer of graphene. Of course, these are in solution form and in this particular bottle, and you can deposit on any kind of substrate to have at least single layer, monolayer, or few layer of graphene sample. Of course, you can use for any kind of applications. So one of the challenges is how you can characterize. I just mentioned, okay, you can just do transparency electron microscopy, AFM, a lot many other characterization techniques. You can see this is the graphene sheet kept on the TM grid. You can see every nice layer which have been seen here. Of course, we can do the AFM, atomic force microscopy, where we can find out the thickness of this particular graphene layer grown by CVD. We see that 1 nanometer. 1 nanometer thickness, it means that are nearly three layers of graphene, right? Okay, of course, one of the powerful, very most powerful technique to characterize graphene is the Raman spectroscopy. So you can characterize this graphene. You can see these are two spectra. You can see the spectra of graphite, maybe multi-layer graphene, and graphene is single layer of graphene sample. Here you can see just left corner of this optical image, right? Exactly here, where I have kept the arrow. Okay, see, this is the graphene spectra, maybe monolayer of graphene or one layer of graphene, and these are multi-layer graphene. How you can see this? Can you see the distinguished characteristic feature? Okay, I can see many features in these two particular spectra. Once this is particular band which is appear around 1530 centimeter inverse, right, or 1600 near to 1600. So this particular band appears because of the stretching of carbon-carbon bond. Because see, this graphene layer is consisted of benzene ring, so they are made of carbon-carbon bond. And this appears because of the stretching of carbon-carbon bond. So this particular bond is known as Z band or E1 to G mode. Okay, so this is another band which is known as 2D band. So this band appears because of the laser frequency which you have used in particular laser, and also because of the number of layers present in your graphene sample. For example, you can see the graphite, this red spectra. You can see this 2D spectra is there. Are you see the intensity of this particular G band and 2D band? There is a slight how much difference? Lot of difference. You can see the intensity here G band is too high. Here it's too less. In monolayer graphene, the intensity is almost 3 to 4 times than that of this G band. You can see here in a particular bulk graphite, in graphite, now there are multi-mode spectra is available. Okay, in single layer of monolayer graphene sheet, now there is a very single fitting or single spectra is available. So this also gives you a distinguished feature whether your sample is monolayer or multi-layer graphene samples. Okay, of course there are some changes in one layer, two layer, three layer, multi-layer graphene. By that distinguished spectra, we can identify whether your graphene is one layer, two layer, or multi-layer. You can see here also the moment we have two layer graphene, you can see the intensity of G band and 2D band. Intensity of G band and 2D band is nearly now similar, and the spectra which we are fitting in single in monolayer graphene. Here you can see there are distinguished spectra. You can see we are no longer able to fit this spectra in a single Lorentzian or Gaussian. We need to fit by multi-layer graphene because now we have two layers of graphene, right? The Raman spectra of two layer of graphene, one layer of graphene, and three layer of graphene is completely different. So by that way, by just Raman spectroscopy, we can identify okay whether your graphene is monolayer, bilayer, three layer, four layer, or multi-layer or bulk graphite. So the splitting, there is a lot of physics behind or chemistry behind it. The basic possible why spectra are distinguished. So this can be described by phonon splitting and band splitting. So a lot of splitting is again explained using double resonant Raman model. So this double resonant model tells that when we excite a phonon, it goes to higher level state, and then once you populated from higher level state, come to the ground level, and this give these two particular possibilities, which is known as phonon splitting and band splitting. So this is the brief about Raman double resonant Raman model. Okay, you can see here, once we have one layer of graphene, two layer of graphene, three layer, four layer, or five layer of graphene, how we can distinguish this particular bands. Okay, again, once we have the very surprising thing, this graphite powder, graphite oxide, reduced graphite oxide, all are black in color. Suppose someone has given you this particular three samples, how you can distinguish? Because they are same in color, how you distinguish? You know, you take bulk graphite, okay, in bulk graphite you will get very single spectra of Z band, which appeared around 1581 centimeter much. You can see very nice spectra for this particular pristine graphite sample, right? Once we have graphene oxide, because now you lose the graphene, right? A lot of functional groups. You can see there are a lot of other functional groups, OH, oxygen, OH, and all these things. What happened? Actually, there will be a this particular we are actually adding defect in the sample, right? So this comes around a D band, which is known as D band, which comes around 1363 centimeter inverse. And you can see this single splitting of graphite, pristine graphite, changes into, you can see the FWHM of this particular spectra is also changes, and the position of the spectra also changes. You can see 1581 centimeter inverse to 1594 centimeter inverse, right? And you will see in addition to that, we also have 1363 centimeter inverse band, which is known as Z band. This band appears because you lose you have converted your graphite into graphite oxide. When you have converted graphite into graphite, we have lot of functional groups. Defects have been added in the material, and this gives you this additional band or peak. Okay, now we have graphite oxide. I want to reduce it to reduce graphene oxide or RGO, right? So how do you do? I will try to remove these particular groups. Okay, still because once you reduce the groups, we are not able to reduce all kinds of groups, right? but you are able to reduce kind of groups. So this we call as reduced graphene oxide, right? Again, you can see the position of this particular Z band. Now here 1594 in centimeter inverse in this graphite oxide changes to again 1584 centimeter inverse to the reduced graphene oxide, right? And we see the D band is almost nearly similar position. And you can see a very important change in intensity of D band and G band. Here graphite oxide, the intensity of G band is more, and in reduced graphite oxide, the intensity of P band is more. Here, we actually introduce large degree of this defect in reduced graphite oxide. Therefore, intensity of P band is much more than graphene oxide. Okay, so once we have this synthesized this material, can you probe it for some kind of application? So here we have used this material, a single layer of graphene for sensing application. For example, molecular sensing application. Okay, so we have this particular two molecule which is known as tetrafluorine and TTF, and this is another molecule tetracyanoethylene, or this in brief which is known as TCNE. So these are very powerful molecules in chemistry. So this tetrafluorine TTF, which is N-type doping, or which is known as very powerful electron donating molecule. So this is the structure of this particular molecule. And another molecule which is known as tetracyanoethylene, which is again P-type dopant or electron acceptor molecules. So these are very strong electron donor and acceptor molecules. So what we have done, we have the kind of device or kind of remote spectroscopy measurement on this single layer graphene. Again, we have chosen these two particular samples. Sample number 1 here, A, is pristine single layer of graphene. You can see here D band. Again, here slight small D band, because small defect in that graphene sheet. And this is Z band, appears because of the stretching of carbon-carbon bond. And this is 2D band, a very nice 2D band. Intensity of 2D band is more than Z band. This clearly indicates this is monolayer of graphene. And I have another reduced graphene oxide, right? Again, this is monolayer, but there are a lot of defects in this graphene sheets. These are again prepared by chemistry method, chemical synthesis method, and I did not hardly find the 2D band here. Again, because of the lot of defects in the sample. So what we have done here, so we have prepared different concentration of these two molecules, for example, TCNE and TTF, and we started adding the this particular molecule on the graphene sheet. For example, I have added TCNE with concentration of 10 to 10 molar, and I have recorded the spectra. So each time I try to add different concentration of this particular TCNE and TTF, and I monitored the Raman spectroscopy as a function of various concentration of these two molecules. What I find, okay, let me go on increasing the concentration of these molecules, either TCNE or TTF, and I have monitored the G band position. So, in graphene, G band, particular G band is highly sensitive on strain effect. Small changes happen on graphene surface, it immediately shows the change in the spectra. You see, so without any concentration, and when I started adding the concentration, for example, here I have started 10 raised to minus 11, increase. You see, when you add TCNA, okay, so G band all shifts, okay, now shifting towards the higher level. And when I start adding TTF, G band shifted towards the lower wave number. So this clearly indicates that when I add TCNA on graphene sheet, so the graphene becomes more P-type or more P-type conductivity. When I add TTF, the graphene becomes more N-type in nature. So again, this is because of the slight change in the band structure, and you can see as we increase the concentration of this particular molecules, and there is a shift in G band position. This is because again because we're actually adding the this concentration degree of concentration or degree of dopant is also changing, and this degree of dopant actually because of the changing degree of this particular concentration gives you slight change in opening of the band gap, and therefore this becomes slightly more P-type, and this becomes slightly more N-type behavior of the material. Again, what happened at the molecular level? Transfer from molecule to graphene, a HOMO of the molecule is above Fermi level of graphene, and in another way maybe transfer from graphene to molecule, this particular Fermi level of graphene is above the LUMO of the molecule. Basically, change in change in G band and 2D band, and then we will change again. I just mentioned local structural change, Fermi level change, like the opening of the band gap, and many things happen. We also tested the device, same material, same thing. We tested in another way. So we have particularly prepared the field effect transistor by using electron beam lithography. We have selected again use this process parameters. I will just not go detail how you can make a device by using electron beam lithography, but slightly. So we need a kind of SiO2 substrate. So we can deposit polymer, expose the polymer with electron beam, develop the pattern. Once we have developed the pattern, you give contact of source, drain, gate, and you can lift up the material, whatever you have coated, and then once you are done, then we have devices ready. For example, like this. This is just before coating, just exactly left, and this is after you prepared the device using electron beam lithography, and this is the scanning electron microscope, and optical image below is the AFM image of that same device prepared. So experiment we have done here is very important. So again, we have tested the device with various parameters like just prepared device, device is kept in vacuum, device is post annealed with acetone, and many other. So the natural device, because graphene is single layer, graphene is ambipolar in nature. So we apply a positive gate voltage or negative gate voltage, it will give you the kind of ambipolar characteristics, that which we have found in your device. So what we have done here, so again we have measured the properties of device in a piston form. For example, okay, this black color is the piston device, and we have started here to adding the different concentration of TCNE. For example, you can see we added TCNE 10 raised to minus 6 molar. You see, we find that there is a slight change in Dirac point. So earlier it was exactly the Dirac point is exactly at 0 gate voltage. When we started adding different concentration of TCN, you can see it has been slightly changes moved towards the positive gate voltage. We started again added more concentration, for example, TCN of 10 raised to minus 2 molar. It has been changed slightly more towards the 20 volt. So the change of Dirac point towards the positive gate voltage, it indicates that graphene becomes more p-type in nature. So this is the experimental evidence that we can make graphene either p-type or n-type. So these are experimental results found on graphene with various molecules, and again the devices are based on transistor, and found that there is a change in particular shift of the device because of the again very strong pi-pi interaction between aromatic rings and graphene. Lot many physics and chemistry happen on the surface of the graphene. Again, we have a few layers of this graphene or reduced graphene oxide, and we have tested them for application like sensor application. For example, we have a device this, and one or few layer of graphene have been kept between this graphene figure or electrode, and this used for an NO2 sensing and ammonia sensing. We also prepared a different type of graphene, which is known as nitrogen doped graphene. So this is prepared by some arc discharge, some other methodology to have naturally nitrogen doped graphene or maybe boron doped graphene. So this also gives, this can be used for sensing purpose. Also tested so kind of devices for long-term stability. We found that devices are stable up to 30 days, and this gives a very stable device performance and can be used for humidity sensing application. Okay, so lot of graphene has a lot of potential. So it can be used for say display application, ink time, because and then barrier materials, heat speed, and many other applications. So lot many science, engineering, technology currently work is going on worldwide and potential, but only disadvantage for electronic industry. The natural one layer of graphene is that particularly the band gap is not available, zero band gap. But people are trying to open the band gap by making graphene, nanomaterials, doping graphene, functionalizing graphene, many things are doing, and they are getting some success in the particular. The band gap opening is in mini electron hole, and so people are now moving towards the graphene-like materials. So can this graphene-like materials useful for the kind of application which graphene cannot do? For example, this inorganic chalcogenoids, for example, MOS2 and other chalcogenoids having the natural band gap, and the band gap can be tuned by depending upon the thickness. For example, see there are no range of materials. You can see graphene almost no band gap. One layer of almost you see huge band gap. Band gap can be tuned depending upon thickness from one layer, two layer, or multi-layer of graphene. Again, we have WSC2, black phosphorus, boron nitride, because it becomes insulated because huge band gap, silicon. You can see natural silicon on these things. So these are basically the electronic material and materials for some other applications. For example, when you talk about the band structure of this 2D, MOS2 you can see the single layer of MOS2. The band gap, you can see the bulk MOS2, and you can see the full phonon dispersion of single layer MOS2. When you talk about MOS2, the band gap of bulk MOS2 is near 1.2 electron volt. The moment you make one pair of MOS2, the band gap changes from 1.2 electron volt to 1.6 electron volt, nearly 1.6 electron volt. You can see, depending upon the layers, you can also tune the band gap of this MOS2. Not only MOS2, there are a range of many materials of this family, and the band gap also can be tuned for these other materials also. Okay, and how you can synthesize this material in a very short chemistry way? So we have bulk MOS2, again bulk MOS2 powder. The 100 gram of this MOS2 powder is available with 5,000 rupees in Indian market. I don't know the current cost because after COVID, this price is before COVID-19. Okay, so we have bulk MOS2 powder, which we have done this experiment I think around almost 11 years back. Okay, so what we need actually, we have bulk MOS2, we have N-butyl lithium. You know, this N-butyl lithium is very strong, we need very careful experiment. So what we need to do, we have to put this MOS2 bulk powder in N-butyl lithium, and they have to take into hexane, right? Reflection hexane for 3 days. So what happened now, this lithium, no, lithium loves this layered MOS2. What happened now, this lithium will, now we have, just imagine you have now this paper, and this gives very nice, now lithium will go inside in between these layers individually. And when you do simple ultrasonication, explosion butter, you will be able to separate out these many layers of MOS2, or maybe few layer to multi-layer of MOS2. Depending upon how you do the sonic ultrasonication and explosion, this will give you how much is the thickness of your material. Again, you can do a pretty simple experiment. You take this molybdenum trioxide powder and this particular salt, KCN, and you can do that. Basically, this is hydrothermal experiment, hydrothermal, right? So you can put hydrogen, so you can put water and heat the hydrothermal reaction with 180 degrees Celsius. Again, keep it for 24 hours and you have a few layer of MOS2, similar experiment. Again, if you don't want to wait for one day, immediately in few hours, you have another chemicals or chemical salt, which is hydrogen MO4 and this particular NH2 CS NH2. So we heat that particular these things in again similarly 500 degrees Celsius in a furnace for 3 hours, and you have a few layer of MOS2. Basically, you can see the schematic how explosion happens in water. Your bulk MOS2 hydrothermal process. So lithium go in between this particular layers and lithium integrated compound. And when you do a simple explosion in water, you will be able to separate out these MOS2 nanosets, right? Okay, suppose you don't want to wait for say 3 hours, so you can have your experiment in just 1 minute. Okay, so we have use here a laser explosion experiment for some other materials. For example, black phosphorus. We also use for MOS2, not shown here. So what we need actually, so we need again bulk powder of any this 2D chalcogenic material like MOS2. We need a gauge beaker. We need gauge optical window because I need to pass the laser through this glass. Okay. So what we need is some kind of solvent. Here I have KOH as a solvent. and I've added that particular bulk material. I have put the laser shot. I have given the laser shot. I'm continuously stirring the solution. I have put some laser shot for a minute, and when I characterize the material, I found that the seed have been exploded in the bottle. And depending upon the laser energy, the time, and all these things, we can actually optimize the how much is the thickness of this particular material. Of course, we can characterize this material by using various other techniques like TM, especially HRTM. You can see the individual this atoms under transmission electron microscope. You can see the hexagonal structure nature of this MOS2 and WS2. So this clearly indicates that the things which we have obtained, these are monolayer, few layer in nature, having hexagonal structure. Okay, can you do it? Can you synthesize the similar material by Scotch tape method, which I have shown you earlier? This material also can be obtained by simple explosion by Scotch tape method. So again, we need a bulk, this MOS2 crystal, WS2 crystal, or whatever, and I can put it on Scotch tape. Again, as mentioned, we can have any kind of SL2 substrate is fine. Here, I have shown you different optical images. This optical image is for MOS2 deposit on 15 nanometer of SiO2. Then this particular D image is for 300 nanometer of SiO2, and this C image is for 500 nanometer SiO2 Si substrate. So MOS2 is same everywhere. The nature is same, like monolayer of MOS2, but thickness of SiO2 has been changed. Because of change in SiO2, my optical contrast has been changed. Because change in optical contrast gives you different color contrast. That I can see under optical microscope. Because when I change the this optical contrast, this particular thickness of SiO2, I can see the change in the color contrast, and that gives you the various other color contrast for the various layers of MOS2. Right? For example, you can see this one layer or multi-layer of MOS2. Of course, we can characterize by AFM and find that so these are monolayer in nature and have similar characteristics and properties. But here I have changed the SiO2 substrate, and therefore the color contrast has been changed. Why this color contrast has been changed, I will explain you in a next slide. So these are just optical microscope, which is again good enough to find out number of layers in MOS2 and MOS2 like other chalcogenide materials. You can see here. So here one layer of MOS2 consists of, okay, here we have okay, one molybdenum atom in between and two sulfur atoms attached to both sides, like upside and downside. So this becomes one layer of MOS2. Okay, so why my optical contrast is changing? Because of the change in SiO2 substrate. So you need to go back to 12th standard equation of reflectivity intensity. So basically this equation is basically consists of, you need to measure your refractive index of your material, that SiO2 substrate which you have taken. For example, we should know the media air refractive index of, once you know the refractive index of air, refractive index of your whatever MOS2, refractive index of SiO2 substrate, silicon. So this gives you a very simple equation which is related to intensity of plate minus intensity of substrates divided by intensity of plate and intensity of substrates. Once you put all these parameters, you can calculate, you will get this particular color contrast. For example, you can see the left top image of SiO2 thickness as a function of wavelength. Again, wavelength also become a very crucial. Whatever wavelength which you are using for optical microscope, generally, so you are using this visible range, right? Wavelength of visible range or that particular. See, depending upon the thickness of SiO2 and depending upon the wavelength, so what is the color contrast I can expect it for the single layer of MOS2. Again, you go for bilayer of MOS2 down left bottom image, SiO2 thickness as a function of this wavelength, right? See, so this is very simple equation. You can solve this equation. You can be define what is the color you are expecting, right? For single layer of MOS2 or any other layer of chalcogenide MWS2, MOS2. But we should know this simple parameters. How much is the refractive index of air, that particular material, SiO2 and silicon. You can put these parameters and you simply calculate how much, what is the color contrast, optical contrast of that particular layer. Okay, sir, these are a lot of calculations, simple calculations done for number of function of number of layers and wavelength. You can see this is again for 50 nanometer SiO2 or 300 nanometer SiO2 or 500 nanometer SiO2. And you can get back the expected color contrast of that particular material. Again, here Raman spectroscopy becomes very powerful. Okay, just Raman spectroscopy also tell you how much is the thickness of MOS here. Important thing to note that after 10 layer, MOS2 behave like a bulk. Means up to 10 layer. Okay, it is in nano region. Right? After 10 layer, it is become like a bulk MOS2 material. You can see as you change the number of layers, you can see for Raman spectroscopy for bulk MOS2 single layers, this gives you basically two spectra. So first spectra is because of the E1 2G mode, where what happened now, your molybdenum atom is moving towards the opposite direction and sulfur atoms moving towards the opposite direction. You can see here at the extreme right corner. And in another case, A1G mode, what happened? Your molybdenum is at stable position and sulfur atoms are moving in a opposite direction. So this will give you A1G mode. So this is A1G mode and A1G mode. So when laser is shining, so this start vibrating and this gives you these two particular vibration mode. And depending upon thickness, for example, you can see 10 layer of MOS2, 8 layer of MOS2, 6, 5, 4, 3, 2. Okay. Another important parameter here to note is that the peak frequency difference between these two peaks. For example, for bulk MOS2, the peak frequency difference is almost 26 centimeter inverse. 26. When the moment you make a monolayer of MOS2, the peak frequency difference changes from 26 centimeter inverse to 18 centimeter inverse. This is also very important and important characteristics to distinguish, okay, whether my sample is 1 layer, 2, 3 or 10. So for 10 layer of MOS2 sample, the difference is 26 and for 1 layer difference is 18 centimeter inverse. So by that way, you can just do Raman spectroscopy of any sample, right? You have prepared by chemical method, prepared by Scotch tape, prepared by CVD, or any method. Just do Raman spectroscopy, find how much is the difference between these two peaks. Okay, it is 26. Oh, this is bulk. It is less than 26. Okay, 26 to 18 centimeters. You can calibrate whether it is 1 layer, 2 layer, or in between layers. You can easily find out. Okay, again prepare the devices based on this particular layers and find that they have ability to be used for next generation kind of devices. For example, we have used here the devices for nanoelectronic devices. When you talk about the devices for industrial application, we need to use the measure the hysteresis in this particular device. Hysteresis is become very important measurement because when you want to make a device stable. For example, I have a lot of devices in my mobile. Like mobile has a lot of transistor. Okay, every time when I switch on or switch off the device, I am getting different login time, right? So this means that the device is not stable, right? So when you talk about the molecular level material or devices with atomic scale, right, they are highly sensitive to the ambient environment, ambient conditions. For example, where we are sitting, a lot of oxygen molecules, right, a lot of water molecules, a lot of other impurities in the environment, they just come and they just sit on this particular material and then give a lot of change in your material, right? Properties of material slightly get changed because of these absorbents. They are coming and they functionalize to these materials because nowadays is naturally highly sensitive materials, right? They start connecting all these materials with oxygen functionalization, water molecules, and all these things, and that way the materials start slowly degradation. So we need to put a kind of layer Once you kind of layer, you will not get the hysteresis in your devices. So that's the experiment which we have done here, and we have made different kind of devices using again by using electron beam lithography, measured properties of devices and find out what is the reason of origin. We have done experiment with vacuum. Okay, can you remove lot of oxygen molecules, water molecules? Yes, we can remove it. Okay, we have done experiment with various humidity and find out, okay, you can see the water level is 60%, 22%, 12%, and dry air. How the stress has been slightly become smaller and smaller, right? Also done experiment with the dark condition and photo condition. I found that also one of the reason for hysteresis. I have coated actually the device with silicon nitride. Okay, silicon nitride coating has to be done in a high temperature and in vacuum condition. So it is expected that high temperature, like more than 300 degrees Celsius, all water molecules have been removed, and very less because this is in a vacuum condition. So a lot of oxygen functionality has been also removed. And once you have taken off the device after coating, and we found that device is giving very nice performance. You can see the mobility measurement before passivation is 1.7 centimeters square per second. After coating, it is 71.8 centimeters square second. So because of now we have improved contact, then because device is also annealed and lot of functionalities have been removed, therefore this gives a better characteristics after coating of silicon nitride. Also done experiment with using self-assembled nanodielectrics. So self-assembled nanodielectrics, because when you make a material pre-defect transistor, we need to have a gate. So this is basically generally a dielectric gate. Okay. So instead of using SL2 as a common gate, here we have made a sand gate. Sand gate is nothing but we have a lot of these materials, like for example sulfur, zirconium, hydrogen. The combination of these materials, the thickness of these particular materials, we have used as a sand gate, or this is a gate electrode. And we have kept a single layer of MOS on this particular sand layer having thickness of 2.4 nanometer, and we have tested the device performance. So this is very simple thing, and found that they have been efficiently used. So I have used again this same material for field effect transistor application as well as sensor based on transistor. Again, this is a very simple thing where we have mixing chamber, tested gas using mass flow controller, field effect transistor based gas sensor device, basically sensor based gas sensor and most based sensor, and we have connected this to K3 semiconductor analyzer. We pass the gas, control the gas, how much is the gas is flowing through your mixer chamber, and depending upon that, you can measure the electrical signal, or maybe you can measure the capacitance of the device and all these things. This many things you can measure. And so these are some measurements. For example, we have tested it for ammonia as a function of, say, tested, because now we have three electrodes. We have source, drain, and gate. So we can particularly use the gate electrode for controlling the sensitivity or just getting the selectivity. Maybe if you apply, say, 15 volt of gate voltage, so we may get a better selectivity or better sensitivity. So that many experiments we have done, and so these are some optimized experiments for ammonia and NO2. You can see in one case the sensitivity is going down, in another case sensitivity is going up, because these are N-type electron donating and electron accepting gas molecules, right? And basically, the moment these gas molecules sit on the MOS two layers, you know, the familiar of this MOS slightly changes towards the towards the conduction band, and because of that, there is a change in resistance. And that change in resistance or sensitivity can be seen in this particular sensor result. You can see also done experiments with various gate voltages. So this basically I need some material may not be sensitive enough to get the good sensitivity. So I need to basically, maybe I can tune the selectivity also. So here I need to optimize how much is my gate voltage. So depending upon gate voltage, so I need to do many experiments, maybe to volt of gate voltage may be good for selectivity purpose or sensitivity purpose. And to some materials are not sensitive enough to detected by the sensor. So I am applying some gate voltage so that that sensor can detect that gas molecules to be present for the sensor. So that can give you some kind of signals. Okay, basically, so what happened at the molecular level? So this NO2 molecule or ammonia molecule just come and they just sit on the this MO2 layer. And what happened? There is a slight change in the Fermi level. And when you talk about the molecular level, you can see the then also photoluminescence and charge density of MO2 because ammonia is N type and this NO2 is P type, right? So what this PL spectra shows you, or MO2 with NO2 ammonium molecule, you can see in particular B figure, we see the charge density difference plots of oxygen, water molecules, ammonia, particularly NO, NO2 and CO on monomer. You can see. So the red which I have shown here, all places is green. Actually, there is actually a distribution which corresponds to the charge accumulation, and the green which I have shown here is the charge depletion. So these are the origin of sensing mechanism happen on the surface of the MOS2. Also done experiment. Okay, so how much is the sensitivity? How much is the sensitivity? So as a function of say ammonia and sensitivity, right? So now here I have changed the number of layers. Okay, I don't know because 2 layer is more effective, or 3 layer of MOS2 is more effective, or 5 layer of this MOS2 is more effective. Here I have a different concentration of ammonia, and here I have the sensitivity parameters. That is whatever coming from the measurement, right? And I have actually a third electrode where I can tune or I can get the selectivity, sensitivity, and lot other parameters. Also, of course, we have done this for ammonia and NO2. Of course, one of the parameters which need to be optimized is the response and recovery time. Right? It's also very important. When we have functional device, we need to optimize these things. And what we have done actually, how to optimize the recovery time. So what we have used actually here, we have used the green laser light or red laser light. When I put the green laser light or red laser light on the device, okay, it just helps to break the bonding between MOS2 and NO2 or ammonia molecules. When bonding between MOS2 and NO2 molecule is very fast, of course, I can expect very fast recovery time. So that's what I have found in my experiment, and find that we can actually tune the recovery time also. So that is very important because in another 10 or maybe another 100 seconds, my device is ready to sense another kind of molecules or another kind of gas, right? So also I have done the experiment to find out the what is the exact origin of the this gas sensing mechanism. So we find that the charge transfer is the origin of this particular gas mechanism. So how we have done this experiment? So we have again put this single layer of MOS2 device, in particular this glass container. Of course, we have put one optical window, and this is gas inlet and this is gas outlet. And the moment first we have done run with the nitrogen or argon gas and recorded the Raman spectra. Okay, we find that the difference between this particular two peak is almost say 18 centimeters. So this characteristic is single layer of MOS2. Okay, what we have done here? So we have added or we have passed the 1000 ppm of ammonia gas through this gas inlet, and we have recorded the Raman spectroscopy. We find that there is no change in the difference, but there is a slight change in the position towards say gate voltage, right? Towards the back side. And you also find that there is a slight change in the FWMHM. So this clearly indicates that because of this happening because of the charge transferring. Charge ammonia molecules, they are just sit on the this particular MOS2 molecules, and this gives you this particular change, right? And this becomes very important. I find that because of the charge transfer, okay, there is a change in the resistance, capacitance, whatever I am monitoring my device. So this is again did it for upon exposure to NO2 gas with concentration from various 1.1 ppm, 200 ppm, and this is so when I compare my sensing result with metal oxide, traditional metal oxide which are studied for almost 30 years back. So here my mobility is slightly low and temperature, again I'm working here with room temperature, and traditional metal oxide, I find that the short response time, right? Here the response is slightly more in my material, and here low energy consumption because metal oxide functions only at high temperature. Here my sensor is functioning at room temperature, right? So that is very important parameter. And again, the mechanical flexibility capability is very good, and this traditional tungsten metal diachalcogenase. But in metal oxide, problem with the long-term stability. You cannot use material for longer time, longer division, because of the oxide. They start oxidizing, and also nano, right? And one of the challenge faced by industry is the scalable fabrication, right? Mass scale production. Again, here, when I compare about the disadvantages of this MOS2 based material or MOS2 like material and metal oxide traditional material devices, here one of the disadvantages is low selectivity. Yes, but of course I can change this selectivity or tune this selectivity by traditional device by changing the traditional device to modern devices. For example, this particular 3 electrode type device, right? I can select improve the selectivity. Again, recovery is a problem, but I have modern instruments, modern techniques, modern technology where I can recover the device. Then, of course, currently because of the there is a cost is very high because we're not doing research on mass production devices. We're working only laboratory, so now cost become very high. Again, one of the problem is lack of long-term stability. So I cannot run this device for long-term stability, larger scales or larger cycles. Right? Again, problem also scalable application because of the lab scale. Because my device is at nanoscale level, and fabrication is of course a problem, right? In traditional metal oxide, disadvantage here again, mobility is very low, and of course they are working only at high temperature, and they need actually high power consumption, and of course low gas response. This is also disadvantage for traditional metal oxide. So what I did here, so can we combine, can we make hybrid materials based on this traditional, this transition metal dichalcogenase and metal oxide, where you can have properties of these two materials. So what we have done here, this is experiment done by hydrothermal method synthesis. Okay, so this is a few layer of MOS2, and we have put it SN2 nanoparticles. By simple hydrothermal experiment, we have done the gas sensing performance. You can see here response with just SN2 nanoparticles and response with SN2 MOS2 nanoparticles. You see in traditional SNO2, when you choose SNO2 nanoparticle as a sensor, what happens? The response is low. You know why? Because when you choose SNO2 nanoparticles, they're always, when you coat on a device pattern, they're always agglomerated in nature. They are not well separated, right? And therefore, they do not found a particular bonding. But when you make a hybrid material, when SNO2 at MOS2, you know what happened now? So this is advantage. You can see this band structure, right? You can see MOS band structure, conduction band structure. There is a, and advantage is that when you coat SNO2 on MOS2 material, there is well separation. This well separation does not allow SNO2 nanoparticle to be agglomerated. When material is not agglomerated, have very high surface area, because your large surface area available. When your large surface area available, your sensitivity, selectivity. So these are parameters which are basically based on these properties of material, right? Surface area, because once your large surface area available, you will get very high selectivity, sensitivity, and of course response and recovery as well. And actually, you can design a band structure of material again depending upon the thickness of your MOS2 and size of the nanoparticle, the traditional nanoparticle like SiO2, zinc oxide, and all these things. So this gives you very better sensitivity and selectivity for these traditional materials. For example, you can see here, right? So response of these hybrid materials, and these are characterization techniques. For example, this is TM images of these hybrid materials, and you can see exactly right corner that how coating of MOS2 is coated on SiO2, and these are well separated SiO2 nanoparticles on MOS2 surface, and this gives basically very high surface area. And because of the high surface area, so for example, you tested here ethanol sensing performance of MOS2 nanosheet, which delivered on SiO2 nanoparticle. And because of this another material, for example, this is very zinc, you can call zinc oxide on MOS2, right? Zinc oxide on MOS2. This is given a very important result. Again, can go up to now just 0.2 ppm level. And again, because of the depletion layer MOS2, the band structure which we have found, and the other characterization, the characteristic feature, like I'm getting very high surface area, well designed, well aligned zinc oxide, which is giving very high important properties, high surface area, and gives very high sensitivity. So traditionally, how you can synthesize this material in your laboratory? Anywhere, in just very simple college where I don't have any facilities. So I take this particular MOS2 powder or WS2 powder, any powder. I just need a very simple ultrasonication. I put the material in ultrasonicator, for example, in some cuvette, and put the material with some solvent, maybe KOH, NaOH, or acetone, or NMP. NMP is best because that gives you a very good result. And I just do ultrasonication maybe for 1 hour, 2 hours, depending upon, and of course, speed is also important 3000, 6000, 9000, or whatever. And of course, after that, you can do centrifugation, and you can separate the subordinate material and sedimentation. And once you have separated out these things, and you can see the color change in color contrast depending upon the speed of your centrifugation 3000, 6000. Because why I'm getting different color contrast? Because the thickness of layers are different in 3000, 6000, 9000, and 15,000, right? So this also gives you thickness dependent properties of the this ultrasonicated atomically thin MOS2 and MOS2 like other material like WS2, MOSC2, WSC2, SNS2, SNS2, and all these things. Okay, once you have these materials, so these materials are in the form of solvent, right? Solution, or we call this as a electronic ink, electronic grade ink. So you can coat this electronic grade ink or inkjet printed, or inkjet printed ink. So you can coat this ink on your electrode. So you have directly just drop course, and then drop course on P pattern device. And of course, here traditionally what we have done here, we have used graphene as a electrode. In between these two graphene electrode, we have put it because graphene is highly conducting. I have put this MOS2 as an ink, and done a lot of testing. For example, how much is the thickness? Just putting initial coating of the layer. Then we have thermally anneal the device. We have photonically anneal the device, and how much is the thickness and all these things, right? Once we have anneal the device, the thickness becomes stable, and then we have done this experiment. You see how surface slightly change when you have done thermal annealing or photonically annealing and all these things. Once your device is ready, you can see ready for the device performance or device testing. So we have use this device as a photo detector. So most graphene photo detector prepared with the thermal annealing. So this becomes very important parameter, right? A very important device, and gives very good performance for this particular device. Again, fully printed MOS to graphene photo detector. Again, annealed by photonic method, and this gives a very good result as a photo detector. Again, we have synthesized this large area of MOS2 like materials by using chemical vapor deposition. So what do we need? Here we need MO3 powder. So we need selenium pellets or kind of selenium source. So and we need actually argon and hydrogen gas, right? Just for activation purpose, right? So once we have this particular, so depending upon the temperature, because we need to evaporate both sources, selenium and MO3, at the same point temperature. Because selenium melting point is around 130 degrees Celsius, MO3 evaporation point is around 450 degrees Celsius. We have to evaporate both materials in the same time, and hydrogen as a reducing agent. So we'll be able to convert MO3 selenium into MOSC2, or depending upon MOS2 we want, MOS2 we want, MOSC2, and all these things. So you can choose the salt or precursor depending upon that. So see, this is simple growth mechanism again. Chemical vapor deposition, you have MOSC or MOSC depending upon what you have taken, MOS2 or MOSC2. You have cluster formation, you have conversion of MO3 into sulfur or selenium nanoparticles, and this go and sit on the surface of the SF surface. When the evaporation point is reached, in a stage first and stage 2, you will have MO through into MOC3 or MOS2 depending upon what second salt or precursor you have taken. So you'll get the layer again. Thickness can be tuned depending upon how longer is your reaction is going on. So this is again optical image and AFM image of that MOC2 layer, which I have grown just by chemical vapor deposition. Of course, again here you can choose Raman spectroscopy and atomic force microscopy to characterize the different layers. Again, I'm getting 3-4 symmetry because 3-4 symmetry is very much dominant as compared to bulk material, because in bulk we have 6-4 symmetry. So 3-4 symmetry is very much easy. With energy required to have a 3-4 symmetry is very less as compared to have 6-4 symmetry. So I'm always getting triangular shape, because the triangular shape, that is nothing but a 3-4 symmetry is much easier because I have a very low energy is required. Therefore, I'm always getting triangular shape. Of course, you can have a different kind of shape also. So you can change the symmetry because you need to have some different kind of energy. So you'll get 4-4, not 5-4 or 6-4 symmetry also. So different structure or different dimension also we can grow on the surface of the your substrate. Okay. Of course, I have choose. You can change the substrate also. Earlier I have SiO2 substrate. I have here gold substrate. Okay, and you can change the temperature also. So depending upon temperature, you will also have different kind of structure on your SiO2 substrate or the substrate which you have chosen. Of course, I can pattern the device and of course measure their electrical properties and some other properties which you find that is useful for your device application purpose. So this is another very similar method. We have here MO3 already coated on your SiO2 substrate. I have sulfur gas, argon as a again carrier gas MO3. What happens? MO3 when you pass hydrogen gas, so you will able to convert this MO3 into MO2 and hydrogen oxygen. This H2O go out in the form of gas. And again, there is conversion of MOO2 into sulfur. Reaction happen between these two, this particular salts, and then you have MOS2 coated on these layers, and oxygen evaporates as a gas form. So this is simple synthesis of conversion of MO3 into MOS2. Okay, of course, this chemical synthesize or any other synthesized materials can be transferred on any kind of flexible substrate to have high performance bendable or substrate. For example, Kapton is a very flexible kind of substrate. You can coat that material on Kapton substrate and use as a flexible device application, which I have shown earlier, right? This can be used for flexible sensor applications. Of course, you do Raman spectroscopy and find that, okay, how much is the peak frequency difference? Here, actually, I have peak frequency difference is 25. This indicates that at least I have 8 to 9 layers of MOS2, which have been deposited on this Kapton substrates. And this gives high performance. Again, I have another method here, which is known as hot wire chemical vapor deposition. So, hot wire means here I have vacuum chamber. Okay, I think I don't have that figure, but here I have vacuum chamber. Suppose I want to deposit a WS2 film. Okay, I need a tungsten wire or high metal wire or electrode. Okay, and in that chamber, I will heat the tungsten wire up to evaporation temperature. What is the evaporation temperature of tungsten? Tungsten evaporation temperature is more than 2000 degrees Celsius. Okay, I will evaporate the tungsten at that temperature and I will pass the sulfur gas. So what happened now? This tungsten and sulfur gas molecular reaction will take place in a vacuum chamber and I have substrate kept down at high temperature and I will be able to grow uniform film of WS2 or you can choose MOS2 uniform. So here I need molybdenum wire or molybdenum electrode. Only thing that you need to evaporate that molybdenum wire or tungsten wire to grow this particular layers. So I have uniform film here, uniform film of MOS2, WS2, and this film is transparent in nature because again thickness is less than 10 or whatever. That's why it is much more transparent. I have done lot of other characterization before I use them for some application. For example, I have done XRD. For example, you can see XRD shows 002P. So this indicates that I have grown a very good single crystalline WS2 layer on this particular SiO2 substrate. I have done Raman spectroscopy also. Raman spectroscopy also has this two particular peak which is known as E12G, A1G. In addition to it, also has some other bands also. Okay, and also the absorbance measure and all these things. I can see the optical photograph and shows that it is not transparent in nature. Now, of course, I have used it for the kind of device which is humidity sensor and photo detector and find that the response of device is just 32 seconds and recovery is 21 seconds. You see how fast is my device. Again, I have option to have optimized the recovery time. I can put laser light or some other thing and I can make this recovery time better. So this fund and one of the advantage of these devices is that so they all function at room temperature. Similarly, I have WS2 device. Again, this is prepared by CVD method. I have characterized using XRD, Raman, and all these things. This also here you can see the response and recovery time is almost 5.3 milliseconds, just in millisecond. Still, I have some option to improve it, but this is enough to have application in kind of devices, right? So here I have done experiment for two-dimensional WS2. Again, experiment with pristine material, experiment with WS2 metal oxide hybrid, and origin or mechanism of the sensing is similar in nature, but here I have potential or I have an ability to have improved device performance. Again, there are a range of materials as mentioned. So this is another material which is known as MOSC2. Again, this Raman spectroscopy of MOS2, and this is single layer MOS2 and bulk MOS2. Can see the difference. And done again, transistor based devices. Mobility is very good in nature, and you can have this ammonia based devices based on this MOSC2. And again, well, this is very important and interesting part. Okay, file patent based on this particular technology. So what we have done actually, we have synthesized this SN2 nanoflates by simple very click chemistry method and found that these are very efficient for alcohol sensing. You know, alcohol sensing is very important part, and we have tested kind of devices and tested on road where the people are drinking alcohol, especially in 31st January and all these things, and found that the response and recovery are in just few seconds. And this few second response and recovery device suggests that this SN2 nanoplates are very good for this particular ethanol, methanol, and IPS sensing application. Then in process transport this particular technology to industry, and they are actually making kind of this alcohol-based sensor devices. Again, can you improve the stability, sensitivity, and selectivity of devices? Yes, of course. The methodology which we have adopted earlier, can you have a composite or hybrid material of SNS2 and SNO2 nanoparticles? Okay, SNS2 is a layered material and SNO2 oxide material. So when you have hybrid material, your large surface area available, large surface area, agglomeration of SNO2 nanoparticles slightly less or much less, and opportunity of improved surface area, and that gives you very good sensitivity and selectivity. Here again, similar materials we have, but we have also file a US patent based on this technology. Can you have electronic grade ink of this material? And this ink just can be simply coated on kind of substrate, and this becomes a device. Again, depending upon the methodology, you can have very good sensing performance of this material. So again, this can be used for say ammonia gas sensing application as well as alcohol sensing application. So another material synthesis which is known as PTAC2, platinum disulfide or platinum diselenide, right? So this is again prepared by very simple this click chemistry method. So yeah, this particular two salts we have used H2PTCl6 HTML. After ultrasonation up to 50 minutes, we have drop faster on silicon substrate and then transfer to a high temperature furnace and for annealing purpose, and then straight away characterize the material. We found that the material synthesis is PTAC2, and we find that, and then, of course, characterize using various methods like XRD, Raman spectroscopy, TM, Raman, and all these things, and found that this material can be used for say sensing application, gas sensing application, for example, humidity sensing application, photo detector application, and all these things. Another material which is known as PDAC2. Again, we have a transistor-based sensor application. Again, material is synthesized using various traditional techniques using XRD, Raman, TM, and all these things, and find that this material also has very good kind of applications, right? Okay, and when you talk about the various techniques, methodology, materials, we found that so we have done use this method. For example, chemical vapor deposition, mechanical explosion, liquid assembly, traditional silicon carbide technology, and liquid phase explosion. So you want quality, you want material, you want quantity. So you can, depending on that, you can choose the methodology, right? So this is quality versus the production. So you can choose any method depending upon your need. Again, very recently we have now this particular borofin, like carbon. After carbon, we have boron. So boron also can be used as a layered materials, and again this can be synthesized by hydrothermal method and this liquid explosion method and many other technologies. And we have, of course, this used as a photo detector application, gas sensor application. Maybe also use surface enhanced Raman spectroscopy. Another material which is known as indium selenide. See, very interesting part I am going to show you. See, when you do Raman spectroscopy as a function of various layers of indium, you can see bulk here. Okay, in bulk Raman spectroscopy of indium selenide, you will see able to see this particular A1G mode, this A1G mode, then A1 mode, right? This is for bulk, maybe more than say a 20 nanometer layer of indium selenide. You see this 12 nanometer, then you can see this 10 nanometer of indium selenide layer, 8, 6, and 5. You can see 3.5 nanometer. Of course, the one layer of indium selenide thickness is around 1 nanometer. Okay, indium, because we have indium in between and selenium on both the sides. This makes you one layer of indium selenide layers. You see, at 3.5 nanometer, all the peaks, all the spectra disappears. No, this was very surprising thing. But we found that iridium found the origin why the spectra becomes disappears. You know, when the bonding between the at 3.5 nanometer level or maybe at 3 layer of this indium selenium, the bonding between indium and selenium so weak, becoming so weak that it is does not allow to show you the this reflecting spectra, because so weak, the bonding is so weak, so are not able to collect the spectra. And this is also very good material for gas sensing application, sensor application, photo detector application. Only characterization, how will characterize 3 layer, 2 layer, 1 layer, because spectra for 1 layer, 2 layer, 3 layer is similar in nature, because bonding is so big, right? So that lot of this transmission electron microscopy and AFM measurement to distinguish 1 layer, 2 layer, 3 layer, of course 4 layer, 5 layer. I can do Raman spectroscopy and characterize the material. Of course, this gives very good mobility based on this device. And this is another material which is known as gallium tellurium. Also, we find the same result for Raman spectroscopy, right? For 3 layer, 2 layer, 1 layer, the bonding between gallium and tellurium becomes so weak and not able to collect the spectra. Again, it has a very good application for say photodetector, gas sensing, and application. We have very recently we have this another material. This is not does not belong to this chalcogenide family, which is known as titanium trisulfide. Again, this is we have synthesis in mass production. Very simple chemistry method. We have synthesized various nano ribbon of this TiS3, nano sheets of TiS3, and used it for various applications. We have done various applications, including gas sensor, photo detector, and all other things. And another set of materials, maybe I will finish it in quickly. This is exactly 5 p.m. and I will try to finish it in, wind up all these things in the next 5 minutes. So another material which is known as 2D black phosphorus, like phosphor. Okay, phosphor. Why it called black phosphorus? Because looking black in color. You see, natural phosphorus which is available in the natural nature is white phosphorus. Okay, who can heat it to 180 degrees Celsius, it converts into red phosphorus. And you can keep it for the same thing, same condition for 1 to 2 weeks. For 550 degrees Celsius, you will be able to convert into violet phosphorus. Okay. In another way, you can pressurize this white phosphorus at say 1.2 gigapascal. You will be able to convert this white phosphorus into black phosphorus. You know, this black phosphorus thermodynamically very stable and advantage. This is semiconductor in nature. That's what we want. Semiconductor in nature. And this semiconductor in nature material now is very good for kind of application. This is as a semiconductor. Okay. See, another advantage is when you talk about the band gap of bulk black phosphorus, this is just 0.3 electron volt. The moment you convert into single layer black phosphorus, the band gap changes from 0.3 electron volt to 2.3 electron volt. This, of course, covering a complete range of this visible spectrum, right? So this has lot of application in many this optoelectronic devices. Okay, so these are just phase diagram. So when you pressurize the material, how you can convert this semiconductors in metal and metal phase. Of course, you can choose the structure for orthorhombic or rhomboidal or just simple cubic, just by giving pressurizing the material. Okay, so this is the schematic structure. We have done a lot of experiment like temperature dependent Raman spectroscopy of this few layer and multi-layer of black phosphorus. Even we have done the of course the various layers also we have fabricated, and then the thickness tuning, band gap tuning as a function of thickness also done, and we are used for the kind of application. For example, the synthesis was done by a very simple electrochemical explosion method, where you need bulk kind of material, bulk crystal, and platinum as a another electrode. We have solvent as a Na2SO4, and then we have of course applied the voltage between these two electrodes. We will be able to exfoliate this black phosphorus into this particular solvent. You can separate it out, and you can have layer thickness and other characteristics done on this material. You can see Raman spectroscopy, AFM, and of course we have fabricated device, transistor based sensor device based on this material, and again also done liquid explosion of the same material, and also used for gas sensing application. Again, the gas mechanism is similar. The charge transfer is the origin of this particular gas sensor based on this material. Also shown you earlier that this black phosphorus nanosheets can be synthesized in just 1 second or just maybe few seconds to 1 minute time, depending upon how much thickness you needed. Of course, then we tested it for gas sensor, photo detector application. Also done, also working on the kind of the colloidal PBS and MOS based solar cell application, and the solar cell performance can be tuned or VSC can be tuned by tuning the quantity or habit structure of PBS, CDT, and of course the most which we have chosen. The final 1 minute I will talk about working on today magazine materials. So today magazine is a family of materials. So you can choose now for periodic table. You can see this titanium, radium, chromium, and this is another with combination of carbon and nitrogen. So these are a rapidly growing family of two-dimensional materials. So on this particular transition metal, carbide and nitride is the combination. Again, this can be synthesized by liquid explosion, CBD, and all other. One of the natural application of this material is the charge storage and sensing applications. So not just good detail. For example, this is the one of the material titanium carbide and TX MHZ monolayer and bilayer of this particular material can be characterized and synthesized just by chemical vapor deposition, by liquid explosion. Of course, the applications are very wide in nature: electrochemical sensor, gas sensor, variable sensor, luminescent or terahertz sensor. And this is another material. We have titanium carbide and TS makes it as a function of uh, gas sensing application. Of course, you can characterize by various techniques like Raman spectroscopy, XRD, and all these things. You can synthesize just by liquid explosion, micromechanical explosion, and many other experiment or synthesis method can be used. Of course, you can characterize by Raman spectroscopy, TM, AFM, and lot many. Of course, you can do XPS analysis to find out the exact concentration of this particular material and all, right? And then we have material in the form of ink. Of course, you can deposit the film on electron and characterize and use for gas sensing application and all these things, right? So these are many things it's possible, and many things are coming up based on these two materials. So what I showed you today, graphene and graphene like 2D materials, there are a lot of materials. There are thousands of materials not yet been synthesized. So there is a lot of opportunity to characterize, to synthesize habit materials based on these materials and can be used for novel devices. I have shown this gas sensor and photo detector application. So I've done a lot of work on supercapacitor battery, and which I have not covered today in the talk. And these are also hydrogen generation is also not covered, but this has potential to be used. And many of these kind of applications also shown in the second part how we can make graphene like materials and how we can make hybrid materials, and then how I showed you how the new materials MXCs are coming up, which has the potential for technological and next generation device applications. What is next actually? So there are a lot of materials which have extraordinary properties, not only 2D materials, composite materials, hybrid materials. So now when you go emerging technology, a lot more need to be learned. For example, very careful studies or careful investigation on defects, understanding of the impact of substrate, the control, doping, functionality. So these are natural pinpoints. So this need to be understand properly, need to be investigate, research on this, need to be done uh, before we just move to the technology point of view. When you continue advancement in the, of course, one of the challenges synthesis, characterization, this will remain all time challenges. Of course, one of the challenges devices at small scale, large scale production, which is critical as we move forward this 2D material science and technology. So I just thank you for this great opportunity to present our very recent work, which has been published in a lot of these good journals. And yeah, so thank you very much.
Thank you, Dr. Datta. Very nice talk, and all recent publications you have shared with participants, and the feedback we have received from them in chat box is very impressive. So there are few questions in chat box. We need to pick. And we use ferrocene, cobaltocene to form the graphene-like acids. It means like a carbon for carbonate, we used to use the ferrocene-based species, pentacene-based species. Your sound is not coming. No, no. Still no voice.
Can you hear me?
Yeah.
Yeah, okay. Sorry, I think I was unmuted. Okay, the traditional chemicals or synthesis process which normally people are used for synthesis of carbon nanotubes, right? The same chemicals also can be used for synthesis of graphene. Only we need to change your reaction parameters instead of getting rolled these carbon nanotubes. We don't have to roll the nanotubes, right? We have flat sheet. So that particular environment you need to create as an experiment, and you can use it. Okay. Next question.
What
Okay.
is sand?
So sand is actually basically a dielectric material consisting of various semiconducting materials, semiconducting and metal. So sulfur, zirconium, ZrO2, and very thin layer. So traditionally we use SiO2. So instead of SiO2, you use as a sand because this is very small layer of this various material. So this is just given a name, sand. So this is a dielectric material.
Aditya Bharadwaj is asking what current areas can still be explored by using vaccines or a graphene.
Basically, graphene, because of one of the disadvantages, only band gap. But this can be used for electrode, then conductive material, coating purposes, right? Charge storage, charge generation, right? And amexin is very good material for charge storage applications. So, of course, battery, supercapacitor, maybe gas sensing application can be done. There are a lot of many areas can be opened up for this MX also.
Okay. You have tested this phosphorus-based allotropes.
Right.
Is similar changes observed in other allotropes? The question asked by Shiv Ramakrishna.
No, we have done it for only, I think, phosphorus we have done.
Okay.
We have done it for carbon, we have done it for phosphorus, we have done it for boron, right? Borophyll, which is known as borophyll. So we have tested, so these are traditional three materials largely studied in literature. So other than these three, we have not done work. So done as a composite like SNS2, MOS2, WS2, and all these things. Only three these allotropes we have studied. Other allotropes of these phosphorus have not been studied.
Deepak Raut is asking, is it possible these multifunctional materials to use the targeted delivery of drugs in humans and animals?
Yeah, this can be used, but we need to see its potential, like how much is the that particular what you need to human testing and all these things, right? The poisonous effect and all these things that need to be tested. Otherwise, some quantity, for example, traditional TiO2, right? TiO2 is very good to have a drug delivery application, but how much quantity? After a certain quantity becomes harmful to the body, right? So that has been done. But I think a lot of biology people are working on borophyll. So they have also, I think very recently they have a Nature paper, targeted drug delivery based on borophyll have been done actually.
Other than this, I am finding only the appreciation in a chat box
Okay.
as a feedback. Pankaj Kumar Singh is asking for your email ID. If you permit me, then I'll share
I have
email ID.
given that. Yes. Please give. Yeah, you can type. I can type here if you want. Yeah, you can type here. My email address is datta09@gmail.com. This is my personal email ID. It's not a problem. I think, right?
Yeah.
Yeah, it has
Yes,
come to
it
chat
has.
box.
Yes,
Yeah.
yes.
Okay. Okay. Any other question?
There are no any other questions.
Okay. Good.
Yeah. Okay. Thank you for your valuable time and valuable knowledge which you have shared with the participants of this FDP. Okay. Thank you. Thank you. Again.
Thank you.
Okay.
Okay, I will leave the meeting, right?
Yeah.
Yeah.